Okay, we're going to start chapter 5. It's very important because it is on integration. Now, in first semester calculus, they generally just start it off, making sure you have the basics down, and then they'll get into more extensive techniques. It gets kind of involved, and they'll go through different techniques in usually second semester calculus. So we're going to just do a couple of techniques. But we'll do 5.1, which is on the concept of antiderivatives, which is the opposite of derivatives essentially. And the indefinite integral. There'll be what's called an indefinite integral and a definite integral. We'll learn about the distinction once we get through this. Okay. A function, capital F of x, they tend to use capitals for antiderivatives. So a function, capital F of x, is an antiderivative. Let me just write it nicer. Antiderivative of f of x if the derivative of capital F is equal to little f of x. Okay, so it's essentially going the reverse process of a derivative. If you go take the derivative of this, you get f of x. If you're trying to go backwards from lowercase f to find capital F, that's called anti-differentiation, and they even mention in the book that that's a term they're going to use. Okay, but anyway, they'll tend to use the same letter. So if the function we're working with is lowercase f, as we've been using as a generic function, its antiderivative we're going to call capital F of x. If we go with a function lowercase g, usually we'll use an antiderivative and we'll use capital G for the antiderivatives. Not always, but it's kind of good to match them up in case you have multiple functions going on. The process. Finding antiderivatives is called anti-differentiation. Differentiation, if you recall, is a term for finding a derivative. Finding the antiderivative is called anti-differentiating. I'll be honest with you, I've never heard that term before, but I can, once I see it, I can infer what it means. The more common term is integration, specifically indefinite integration. So that's a more common thing, is to refer to this process as integration. Okay. I wrote that too big, so I don't have space. I'm going to do a real quick example just to make sure you understand the relationship between lowercase f of x and its antiderivative capital F of x. So we're just going to verify. Verify the following functions. Are antiderivatives of f of x is equal to x squared plus 10x plus 7. So I'm going to function, and then I'm going to give you antiderivatives, and we're just going to verify that they bear this relationship. Just to get you a feel for what's happening. Okay. I'm going to use capital F, but since I'm going to do between two of these, I'm going to label them with subscript. Capital F of x1, capital F1 of x is going to be equal to 1/3 x cubed plus 5x squared plus 7x minus 2. And that's an antiderivative. That is an antiderivative of that. What is, because you got to trust me for now, but we're going to verify it. And we're going to verify that when we take the derivative of this, I use a prime notation, where we could also use this notation. Doesn't matter. I could write f1 prime. Harder to read on a board. I'm worried unless you can't see it, but it doesn't matter. And I'm going to just take the derivative of this, find what I get, and it should be, if this is an antiderivative of that, when I take its derivative, I should get back that. So let's see. I'll do it slowly because I want you to see like how it works. So when we do the rules for antiderivatives, you get a feel for why things are the way they are. The one thing I'm going to bring down, but then I'm going to do the power rule on that. Just power rules. A lot of this is going to be polynomial, so it'll be a lot of power rules. I'm going to get 3x squared for the derivative of x cubed. I will bring that 5 down, and then I'm going to do the power rule on the x squared. That would be a 2x. Normally I would multiply these mentally, but here I do want to look more closely at what's happening. The derivative of 7x is just that constant 7, and the derivative of that negative 2 is 0. So I'm going to clean it up now, but notice that this 3 cancels with that 1/3 to give me a clean x squared, which is what I wanted. That's why that 1/3 is necessary, because when I take the derivative, I don't want a 1/3 there. I have nothing there other than a 1. So when I take the derivative of this to get a coefficient of 1, I need to cancel that 3 that's going to come down with the 1/3. Anyway, 5 times 2 is 10, so I'm going to get plus 10x. And then plus 7 from that 7x, that's how I'm getting that 7 there. And then the 0, that constant 2, when you take the derivative, that constant negative 2 rather, when I take the derivative, becomes 0, and it gets wiped out anyway. And so that's f1 prime of x right there. And that confirms. I'll say yes. Well, I don't need to give me an answer, but okay, so that confirms that this function f, capital F of 1 of x, is an antiderivative of that, because when you take the derivative of this, you get back the original function. Okay. I wanted some space over there, but I didn't give me enough room. I'm going to do f2 of x over here. You want, I can call this a and b. f2 of x, capital F of 2, a different antiderivative. So it's going to be 1/3 x cubed plus 5x squared plus 7x plus 13 plus 13. Okay, this one I'm going to do a little more quickly because obviously you can see most of the pieces are the same. When I take a derivative, I will do those mental computations to speed it up. Bring the 3 down, that cancels, so I'm just going to get a clean 1x to the second power. This one I'm going to bring the 2 down, I'm going to get plus 10, x to the 1. That becomes just a 7, and that gets wiped out, so I don't have to worry about the 13. It becomes 0 when I take its derivative. All right. And that's a derivative of f1. That's a derivative of f2. They both have this as their derivative, so they are both antiderivatives. Notice that it didn't matter about this constant on the end. It didn't matter if it was -2 or a 13, because when I take the derivative, it gets wiped out. So I could have had a 13, a -2, I could have a 5 or a 0 or any value there for my constant term. But the other pieces all have to be this. I don't have a choice. I can't mess around with that and change it to 9x, because then I won't get a 7 there. I can't change this because I won't get an x squared unless it works out perfectly the way it did in both of these. So these terms will be the same for any antiderivative, but that constant term can be arbitrarily set. So that leaves us to what they're calling the fundamental property of antiderivatives, which I've never heard that term, but I'll go with it. I mean, I know the property, I've just never heard this term, or this title for it. Fundamental property of antiderivatives. If f of x is, and that's why I wrote an antiderivative, because there are infinitely many of them. If f of x, capital F of x, is an antiderivative, of lowercase f of x than any other antiderivative of lowercase f of x has the form capital F of x, that one antiderivative, plus some constant c. So for some, and they'll sometimes call it an arbitrary constant sum. I'll use that in parentheses. Arbitrary, meaning it could be anything. C. Okay. It's also called, sometimes we just refer to it informally as the arbitrary constant, but formally it's called the constant of integration. I'm hoping that you could see that. What happened? Okay, I don't test you on those terms, but they use, it could come up. Okay. All right. So if this is my original capital F of x, then this is just that same function, but plus 15. You could just tack on a c to that, any c, and it'd be also an antiderivative, and I could choose to tack on plus 15, and when I simplify it, I get that function. I could change it to 16, or I could do anything there. So it's arbitrary, the constant of integration. I'm going to take a moment, even though you're not going to be tested on this, to kind of explain why, or what's happening with those capital F1 and capital F2. I have to erase it so I can draw a little mini graph, a very rough sketch. But that first function, F1, had a constant of -2. The function itself kind of looks like this. This is not an easy record. I did graph it, so I do kind of know what it looks like. And it's passing through 0, -2 as the y-intercept. The other one had a constant of 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. But it was just the same term, so the same function, other than it had a different constant, which means that it's just a vertical shift of that other one. So this is a rough sketch of capital F1 of x. That's a rough sketch of capital F2 of x, passing through a y-intercept of 0, 13. Okay, we're not graphing accurately. I'm not doing low mat extreme or concave or anything like that. But I do want you to remember, and we didn't really emphasize this because it came up in college algebra, how that different constant on that last term just causes a vertical shift. It was this shifted up 15, like I talked about earlier. Anyway, the main thing is the derivatives of F1, capital F1, and the derivative of capital F2 are just the slopes of tangent lines. And because these are identical other than a vertical shift, the tangent slopes for given x's are identical. Let me see. Let's say it's 1, 2, 3, 4. Let's say it's -4. The slope of this tangent line would be capital F1 prime at -4. This would be capital F2 prime at -4. And they'd be identical because they have the same slope, and therefore they would have the same derivative. They'd have the same derivative here. They'd have the same derivative there, and therefore at any point x, those two have the exact same derivative, which was the lowercase f of x that I introduced in that problem. So that's what's happening there. That's why both of these would be an antiderivative, despite that vertical shift or that arbitrary constant there. Okay, that's more theoretical. Let's go more practical now. I'm going to summarize the terms. An indefinite integral. I'll give me any more room. here. Okay, so the notation for an antiderivative is in what's called an integral symbol. Looks like this. It's like a big kind of narrow S. It's technically supposed to be like an S almost, a fancy curly S. We're going to put f of x there. They do have a little notation that's part of it, dx. We'll talk about that, but not too extensively. That's, again, more theoretical. Okay. So this is how we're going to write it. So we'll see examples in a bit, but for example, that first example that we wanted to find the antiderivative of, we would have wrote x squared plus 10x plus 7 dx. We have our function there, and we're capping off with the integral symbol and what's called a differential dx. And that's just notation that's telling you to take the antiderivative of that lowercase f of x. And when we do it, we'll get our antiderivative, which we're going to call capital F of x plus c, and that will encompass all those capital F's with arbitrary constants, f1, f2, anything with any arbitrary constant, but that'll be part of your answer. And we'll see in a bit. But anyway, that's how it would look if we were working on that first example. To contrast an indefinite integral with what's called a definite integral, we will not cover definite integrals until, I think, 5.3. We're going to grind out finding antiderivatives first. Oh, so anyway, taking the integral is the same thing as finding the antiderivative, to the point where people stop saying finding the antiderivative. They tend to say integrate it. So that process will be written out like that. And we're going to learn some rules to be able to do that, to find those antiderivatives. So far, I just gave them to you. And then when we get to 5.3, we will apply those same techniques to a definite integral, which will have the same notation, except it will have boundaries. A little number there, a number there, and we'll talk about what those mean. But once we see that, that's called a definite integral with actual boundaries or limits of integration. And then instead of getting a function at the end, we'll get a numerical answer that we'll get by taking the antiderivative and plugging in b, the upper bound, minus a, the lower bound. And then those will be numerical answers, and we'll get an actual number for our answer for the definite integral, which has a meaning, which we're going to get to when we get there. But anyway, I want you to see this now so you understand the distinction between the two. For 5.1, 5.2, we're just going to learn how to do indefinite integrals and find antiderivatives as functions. We'll worry about that later. Some terms. Oh man, I'm going to go up here and do them. Sorry. Some bullet points. The lowercase f of x is called, just some terminology associated with that. The main ones that I expect you to hear in the future. F of x is called the integrand. X is the variable of integration, and that's relevant when you start getting into two variables, multi-variable calculus, where you have x's and y's, and you have to specify x is a variable integration, or you're integrating with respect to x. What else I got? I've already mentioned it. C is a constant of integration. A and B here are called, well, I'll write it in now, but I'll probably come back to it in 5.3. The lowercase a and b, and that's going to be an interval from a to b. So a to b are the limits, not the same as our usual limits or bounds of integration. Okay, but we'll come to that. Main thing, constant integration or arbitrary constant, that plus c. The variable integration, we're just going to be having x or t or one variable, so that won't be an issue. Integrand's a function we're trying to do the integral or I find the antiderivative of. So just be familiar with those terms. Let me pause it because I got to answer a question for someone. Okay, some properties of integrals. We're going to do properties of integrals and then some rules for some common functions, specifically polynomial functions. There'll be a power rule. Properties of integrals. And this is not finding the antiderivative yet. This is what you can do to manipulate it to make it easier on you. Similar to the properties for derivatives. If you have a constant out front times a function, you can just pull that constant out and just focus on finding the antiderivative of that f of x. So that k will be multiplied by whatever antiderivative you get. That'll be for any constant k. We had a similar thing for derivatives where you would just bring that derivative, that constant down. There's not many properties for integrals. If you have multiple terms that are added or subtracted, I'm going to combine some formula and difference, sorry, the sum property and the difference property into one. But anyway, if you have one function plus another function, you can just do each one separately. So it would be integral of f of x plus the integral of g of x separately, and then just add those results afterwards. If it's minus, then you'll be subtracting those, so if it's plus or minus here, it's plus or minus there. All right. And note that that's only for a sum or difference. There is no rule as of now for anything where it's multiplied or divided. So there is no product rule or quotient rule for integrals. So we have to be conscious of that when we do these. Okay, next we're going to do rules for integrating common functions. And k is still going to represent a constant, and if you just are integrating a constant function, literally just like integral of just 2, your integrand is just 5, your antiderivative is that constant times x, it'll become the coefficient of x. Plus the arbitrary constant integration, we're going to throw that into all of these rules. That'll be part of every antiderivative I write down. Do I want to title these? I do want to title these. You don't need to know the titles, but sorry, let me backtrack. Might use them, especially early on when I'm talking about it. Later on, we just start doing it, and you get used to it. Constant rule, same thing that I just wrote. Power rule is important. Well, that's important too, but the power rule is what we're going to be doing a lot of. And this is for any power, well, not any power, but we'll talk about it. Any x to the n power. What you're going to be doing, since it's a reverse process of taking a derivative, if you recall, the derivative, you're bumping the power down, you subtract 1 from the power. We're going to have to go the other way and increase the power by 1, but then the verification won't work if you don't offset it when you bring it down. So you'll have that 1 over n plus 1. If you recall, in the early part, yeah, I'm going to do it now. That one where I verified the antiderivative, I gave you the antiderivative, it was 1/3 x cubed. So I said verify that that function is an antiderivative of that function, and we verified it by taking the derivative of this piece. It had other pieces, but I'm focusing on this. If it doesn't have anything here, you want a 1 there. When you bring that power down, you need to cancel with that. So that's what's happening there. If that's a square, you're going to have a 3rd power, but to offset it, when you take the derivative, it needs to cancel it there, so you have to have a 1/3 there for it to come out clean. So anyway, that's going to be a factor that we have to worry about. Plus c. And an important thing is that that works for any power n except for -1. And we will talk about that. But every other power other than -1 will work. And that's all for the polynomials we dealt with. So in chapter 3 we would have just had that available. We did do logarithmic and exponentials in chapter 4, the derivatives of them. So that means we can do antiderivatives, which is just a reverse process. So if you recall, the derivative of, I'm going to just write it, the derivative of ln of x was 1 over x. And what that means is the antiderivative of 1 over x dx is equal to natural logarithm of x plus c. And sometimes because logarithms can only take positive values, you can't plug in negative values, they will write an absolute value in more theoretical classes. I'm not worried about that, but be aware that they will do that in other classes. But we'll go with that. Antiderivative of 1 over x dx is equal to ln of x plus that arbitrary constant. And that's because the derivative of ln is 1 over x. You can't at this stage do antiderivative of ln of x. That is nothing that we can handle right now. It's not 1 over x. We don't know what that is. That'll be a later thing in the next semester. Exponential rule. The derivative of e to the x was e to the x. Therefore, the antiderivative of e to the x is also e to the x plus the constant of integration. So those are the rules for antiderivatives that we're going to be using in this section. And the homework that I'm going to assign is just you grinding them out. I'm not doing applications until the later sections. But anyway, you would check it by doing, and we're going to do it with actual numbers, but you would check it by doing the derivative. So if this is the antiderivative of that, you should be able to take a derivative and get back that. So the derivative of a constant times x, the coefficient times x is just that coefficient. Here you would do the power rule, so you'd bring the n plus 1 down, cancel with that, and drop the power down by 1 and get x to the n. Derivative of a natural logarithm we just learned is 1 over x. Derivative of e to the x, the exponential is just e to the x. So that's how that's going to work. And let's do some examples. Okay, let's do some examples. I wanted to mention, so the derivative of natural logarithm is 1 over x. You can't plug in negative values or 0, so it only applies to positive values. But in this way, when you do the antiderivative, the x could be negative, and so sometimes they'll put the absolute value if they're worried about that. They don't always do it, but that is something that you might see there. I don't think it's really going to come up in the problems we're going to be doing, but it may in a future class. Anyway, these are our 4 rules that we're going to be applying, mainly polynomials, and you'll encounter these occasionally. But let's do some examples. Let's see. Find the indicated integral. Will be the instructions in the book, our book at least. The other instructions that are equivalent, they might say evaluate the integral or something to that effect. It does give as part of the instructions to check your answers by differentiation. We did it in the beginning where I gave you antiderivatives and I just had you verify that they were by taking the derivative. And here you're going to work the problem yourself, but at the end you can verify your answer is correct. Is an antiderivative by differentiating. I'm going to mention that's optional. I'll do it a couple of times, but I'm not going to do it every time. As long as you are confident that you've used the rules properly, you're good. This is just purely to catch any mistakes you might make. Okay, let's do our first one. It's going to be a polynomial, so we're just going to be following mainly the power rule. Integral of 4x cubed minus 6x squared plus 5x minus 1 dx. And so the integral symbol and the dx are just capping off. That's just notation for capping off your integrand there. And then when we take the antiderivative, we will drop both of those and just have a function with a plus c. So let's start working it. We're going to be applying this rule and some of the other properties. So first of all, we're going to go term by term using that fact that we can break up a sum or difference. I can also bring down the 4 and just focus on the antiderivative of x cubed, which means I gotta bump up, oh my god, I wrote it wrong. I gotta bump up the power by 1 and then divide by that power. When I wrote it earlier, I had it as a coefficient, but sometimes I'll just cram it underneath. Depends what is good for you. Anyway, I've gotta increase that power by 1, so it becomes x to the 4th. And then I gotta divide by that power, so that right there is the antiderivative of x cubed. Next, I'm going to bring that 6 down, the negative 6 down specifically, and I'll take the antiderivative of that x squared. Got to bump up the power by 1, and then divide by that power, so it's 1/3 x cubed, or x cubed over 3, either way you write it. And then 5, I got to do the same thing on that x to the 1. That's essentially an x to the 1. And I got to increase that power by 1, so it's going to be x squared. And then divide that by that power. Last one, a -1 constant. Technically, I could follow that rule. That would be an x to the 0 power, and the rule still would work for that, but it's also written as a separate thing for just a constant. The antiderivative of a constant is a constant times x. That -1 becomes a coefficient of x. And then you got your constant of integration that you're supposed to put on every single answer for any indefinite integral where you're just getting the antiderivative function. It has that arbitrary constant. It's one of those things like units when you have an answer that's like 24 square centimeters, and if you forget to write the square centimeters, sometimes they'll mark you off some points and say, you know, units are important and don't forget to put units, and you forget anyway because it seems like a minor detail. That's a similar thing. It's technically supposed to be on every answer. You may forget it, and if you do, it's a matter of how much of a stickler your professor wants to be on whether he marks you off or not. So be careful if you're trying to get, you know, hundreds on perfects on every score for any math class you take in the future, Math15. Put that there for your indefinite integrals. All right, let me finish this up. I'm going to just reduce all these coefficients for, that's like a 4 over 1. And that's going to cancel, so I'm going to get x to the 4th. 6 over 1 times 1 over 3, that's going to cancel, I'm going to get minus 2x cubed. That one I can't reduce, so I'm going to have a fraction as a coefficient. 5 halves x squared minus x plus c. Rattling that. Okay, and that should be my answer. I didn't label things, but if I call that lowercase f my antiderivative, I've been using the custom of using a capital letter. I'm only going to label it that because I want to take my, I'm going to do my checking. I'm going to do the optional check on this one. So let me go ahead and take the antiderivative, let me go ahead and take the derivative of capital F. I'm going to do the derivative, and when I do that, I should get back the original integrand if I did it correctly. So this is the check. The derivative of this should be my original integrand. I'm going to do my power rule real quickly. 4x cubed. That one I'm going to bring the 3 down. It's going to be minus 6x squared. Bring the 2 down. That cancels with that 2, so I'm going to get 5x minus 1 coefficient. The c becomes 0 because that's just a constant. And that's what I get when I take the derivative of my answer. And is that my original integrand? Yep, I'm good. So that confirms that is my answer. All right. Any questions? All right. If not, we're moving on. All these examples, as I said, there's only 4 examples, but they have a lot of terms, and I'm going to address all the little things that can come up by going term by term. Let's see. These are going to be long, so I don't have room for this. I'm going to erase. All right. Next problem. So that was your basic power rule. Nice whole number powers. This one not so nice. I'm going to be doing cube root of x minus 3x square root of x minus 6 over the square root of x. A lot of radicals in this one. And a lot of x's, powers of x in the denominator of expressions. Plus 7 over x minus 2 over 3 x squared dx. So that whole thing is my integrand. Again, the dx and the integration symbol capping off the entire integrand. If I had stuff out here, like plus x to the 9th or something, that would be separate. This is indicating that this is what I'm integrating from here to here. find the antiderivative, and I'll just tack on that if I was combining with other stuff. So that's telling me which where my integrand ends. Okay, that's what we're doing. And it's all power rule stuff, except that it's not written in a nice form where we can just apply that rule. We have to reinterpret radicals as powers, and all the x's on the bottom can be reinterpreted as powers of x. So let's do that first. Now, because I'm not taking my antiderivative yet, I'm still going to use my symbol. I'll only drop it when I'm ready to take my antiderivative, which I'm not going to do here. I'm going to rewrite this. Cube root of x is just x to the 1/3. That's just rewriting it. I'm going to take a little moment to mention how to resolve this. That can be written as a single power of x. That is x to the 1 for that x there, and then times x to the 1/2 for the radical. Combining those as a single power, I would add those exponents, I will get x to the 3/2. So that's a power. I'm going to erase this, but that's how you have to combine it into a single power of x. 3/2 power. With this minus 3. This is I got the minus 6 there. That x is the square root, which is half power. It's on the bottom, which makes it a negative half power. All of these x's on the bottom now, they can be written as negative powers. X on the bottom, x to the 1 on the bottom is like x to the negative 1. The 2 and the 3 stay as is. That's just going to be a coefficient of negative 2/3. And that 1, I'm left with 1 over x squared essentially. I'm thinking of it that way, separating out the numbers and the power of x. That 1 over x squared can be rewritten as x to the negative 2. And that's the way I want it. I need a dx there technically, and that's still telling me that I still need to take the antiderivative. Again, all I did there was rewrite it. I'm ready to do my power rule. Alright, x to the n, I gotta bump up the power and then divide by that power. A bit trickier with fractions, but here we go. I'm gonna add 1 to that. 1/3 plus 1 is 4/3. And I'm going to be dividing by that power, meaning I'm going to be dividing by a fraction 4/3. That means in the next step when I simplify, I'm going to flip that, do the reciprocal, it'll be 3/4 x to the 4/3. I can do that now. I'm not going to do it now because I don't want to skip too many steps, but if you, later on, if you're comfortable, you just go ahead and know that it's going to get flipped and become the reciprocal on that fractional exponent. Alright, next I'm going to bring that 3 down, and then I'll just work on that. I'm putting parentheses so you can clearly see the constant multiple and then just work on that. You don't have to, you can skip as many steps and do things mentally if you want. But I'll be careful here. 3/2 plus 1 is 5/2. You need a common denominator if you're, not a little bit shaky on that. But anyway, 3/2 plus 1 is 5/2. I'm going to be dividing by that 5/2 power. I'll be doing the reciprocals next step. Alright, minus 6. Be careful, this is a negative half, so when I bump that power up by 1, negative 1/2 plus 1 is a positive 1/2. And so x to the 1/2 over 1/2. Okay, let's talk about this 7x to the negative 1, because this one is, even though it's in the middle of this and it looks like all the rest, is actually very different, so let's talk about this. If I try to do the power rule, I would do negative 1 plus 1, which is 0, divided by 0, and that's not a thing. That's an undefined expression. Why is this one an issue? It's because that technically is not a power rule situation. Because that negative 1 doesn't work in this formula. That's why the rule, the power rule that we just mentioned, specifies that it only works for values that are not negative 1. Oh my god. I can't believe I messed it up. Okay. Anyway, I have to fix that. It's fixed now. Yes. Okay. So it doesn't work for powers that are negative 1 because of that exact issue. So what do we do in that situation? That is addressed right here. It's 1 over x. So let me backtrack. Out of all of these, writing them as powers of x was a good strategy, except for this one, because that's the one that the power rule does not apply. I should have left that as 7 times 1 over x, because now I'm going to be taking the antiderivative of the 1 over x, and that is a natural logarithm. So this one is a different rule. I'm bringing the 7 down, and antiderivative of 1 over x is natural logarithm of x. And again, sometimes they put it in absolute value, sometimes not. You can or you don't have to, I don't care, as long as you know that that one is not a power rule, it's a derivative of ln of x, meaning its antiderivative is ln over x. Alright, moving on. This one is a power rule, so this one applies. Be careful with this one. You're adding 1 to a -2, that makes it -1, and you're dividing by that -1. That's a power rule, and you get the plus c, obviously. So be careful with anything that just has a single power of x on the bottom. That's a different rule entirely. I'm going to clean up. Doing reciprocals, 3/4 x to the 4/3. That's going to flip up and it's going to be -6/5 x to the 5/2. That's going to flip up and give me -12 because it's going to be 2 over 1 times the 6, x to the 1/2. I can rewrite these as radicals, or I don't have to, which I'm not going to. Plus 7 ln of x, or 7 ln absolute value of x. That one, the negative will cancel, so I'll get plus 2/3 x to the -1. Maybe I want to rewrite that as x on the bottom, but maybe not. I don't care. I can leave it as x to the -1. Plus the c for full credit. I'm not getting deducted minor petty points. Alright, that's it. I could check it and make sure I get my enneagram. Do I want to do that? No, I definitely don't want to do that. Just be careful. This is very prone to little tiny errors, and I'm not that concerned about it as long as you understand. Main thing is you recognize that as very different from the others. So be careful about that. It looks like a power rule situation. It is not when it's a -1 power. Okay. Next, we gotta talk about some weird looking enneagrams that we just have to work with and simplify and rewrite for us to be able to tackle them. So next one is going to be integral of x to the 5th times 3x plus 1 squared dx. Okay. Now, one thing you cannot do is just take the antiderivative and the antiderivative of these two pieces and then multiply them together. That is not a rule. There is no product rule for antiderivatives or integration, so that is not a thing. So you're not going to get x to the 6 over 6 at any stage here. Yeah, it's weird because you got a product of two functions that's squared. How do you handle that with a function inside? Derivatives, it would be a chain rule situation and a product rule. There are reverse ways of doing antiderivatives of that. There are techniques we're going to learn later. For this section, this is all we got. What you want to do is you want to use a power rule by expanding that. That's just going to be a polynomial when you expand it. It's not that bad. I'm going to do it kind of quickly and skip some steps though. I would have to literally FOIL this out. Be careful, it's not just 9x squared plus 1, because you got to FOIL and do the inner and outer, and it's going to have a 6x term in the middle. So you can't just square the 3x and the 1, that's not how it works. You need to multiply out 3x plus 1 times itself and do all of that. And when you do, you're going to get 9x squared plus 6x plus 1. So I'm expanding that 3x plus 1 squared. I still want to make sure you don't try and do x to the 6 over 6 and then do the power rule on that and do 9x cubed over 3 and whatnot, yada yada, and just do the antiderivative times an antiderivative. Again, does not work that way. And again, I just need to get powers of x all just added together. So I'm going to distribute. Again, just multiply the whole thing out, the whole integral. I'm going to get 9x to the 7th plus 6x to the 6th plus x to the 5th. And now I have just a polynomial that I can apply the power rule to. I don't have to worry about the ln in this situation. They're all nice positive whole number powers of x. And I'm going to fly through so quickly, but that's the idea. You gotta, for now, you got to expand it. There are other techniques that we'll learn, but for now, this section is just, you see a situation like that, you got to FOIL it out. All right. Bump that power up by 1 is 8 divided by 8. Bump that power up by 1, 7 divided by 7. And that's 6 over 6. Plus the c. 9/8 x to the 8. Plus 6/7 x to the 7. Plus 1/6 x to the 6 plus c. And that's it. That's how you have to handle it. Basically FOILing it out to get a polynomial not products of factors. You don't want things in factored form for antiderivatives. Okay, in a similar way, here you have e to the x minus x over 4. And initially, that's a weird one. There's no quotient rule for this. You can't do the antiderivative and the antiderivative at the top and bottom and just put them over each other. There's no quotient rule here. You have to, again, think of it similar that way. If you have an x on the bottom, you gotta maybe chop it up and then reduce. Here it's a constant, so I want to essentially break up that fraction into two separate terms. Break up the numerator, rather, into two separate terms, each over their own denominator, so that I can then do it term by term. And since it's the 4 on the bottom, that's just a coefficient of 1/4. 1/4 e to the x minus 1/4 x. That's how I'm rewriting it. And because I'm just rewriting it in a different form, I'm still keeping my integral symbols there until I'm ready to take my antiderivative. And I'm ready to take my antiderivative. So here I'm going to drop those, that notation, and start working my antiderivatives. Let's see what I got for e to the x, my first exponential. And because the derivative of e to the x is just e to the x, the antiderivative of e to the x is e to the x plus the constant integration. So that's what I'm going to do. Bring the 4th down. And the antiderivative of e to the x is just e to the x. This is the power of x. I got to do the power rule. X squared over 2, bump it up by 1, divide by that power, and add on the plus c. Final answer, 1/4 e to the x minus 1/8 x squared plus c. You can write these in different forms, but I'll be just, most of the time, just write as a coefficient times the power of x or a function, even if it's a fraction. But you could write that as x squared over 8 and e to the x over 4. It doesn't matter. All right, but don't forget your constant c. That's it. We mostly powers for now. We're going to learn other techniques in future sections. Exponential came up once. Logarithm came up once. We'll see more of it when it gets incorporated into other things. All right, that's it for 5.1.